Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 12, and we are on Section 2, Chemical Equilibrium, and this is Part 5. Today we are going to discuss the equilibrium constant. So, the equilibrium constant is a constant that relates the concentration of products to the concentration of reactants at equilibrium. So let's talk about this a little bit more. So it's a constant, so it's a number that doesn't change, and it relates the amount of products to the amount of reactants. And once you hit equilibrium, there's always going to be a certain ratio depending on the reaction. And that ratio is our constant. So for a specific reaction and a given temperature, the equilibrium constant will always be the same. So for example, with our reaction with nitrogen dioxide and dinitrogen tetraoxide, there is, for each given temperature, a specific equilibrium constant, and that's always the same. And then it would be a different equilibrium constant for our reaction we were looking at with sulfur dioxide. So let's look at this a little bit more. So let's look at this generic chemical reaction. We have coefficient of reactant A plus coefficient of reactant B reacts to form coefficient and product C and coefficient and product D. So this would be like a 1 or a 2 or whatever your coefficient in how many moles are in the balanced chemical equation. Okay, so please write that down and then let's talk about this. So K is our constant. Our equilibrium constant is equal to the, and these brackets mean concentration, the concentration of product C raised to the exponent of its coefficient, and then the concentration of product D raised to the exponent of its coefficient, all that divided by the concentration of reactant A raised to the power of its coefficient times the concentration of reactant B raised to the power of its coefficient. So the concentration of C, and these little brackets, remember, mean concentration in molarity, which we talked about in Chapter 9, of the product raised to the exponent of its coefficient. So if this was a 2, this would be squared. And if KEQ is large, the products are favored. So if you have a big number here divided by a little number, you're going to get a big number here, and that's because we have more product. If the opposite is true, if we have a little number here, we don't have a lot of product, but we have a lot of reactants still at equilibrium. It'll be a little number divided by a big number, and that gives us a little number. And that, so if KEQ is little, that means our reactants are favored, and we have more reactants at equilibrium. Let's take a look at our book. Looking at page 389, we see that our equilibrium constant is equal to our concentration of product C, coefficient, the concentration of product D raised to the coefficient, all divided by concentration of reactant A raised to its coefficient times concentration of B raised to its coefficient. So let's look at that with some numbers on the next page, 390. So looking at our equation, a reversible reaction, dinitrogen tetraoxide is in a reversible reaction with nitrogen dioxide. And we can see that this is the product, so that goes on this side, and its coefficient we put there, so it's squared. And then our reactants, the molarity goes here, and it has a coefficient of 1, so we would have a power of 1 or just nothing. And then if we look on the next page, we have a couple of different scenarios. So we have nitrogen gas reacts with 3 moles of hydrogen gas to make 2 moles of ammonia gas, and then here's our certain temperature. And you can see we have different concentrations of all of these different compounds. But when we do the math, our equilibrium constant, our K, all ends up to be about 0.0602 or 3. And so, because it's the constant is just that, it's constant, and at equilibrium, the ratio of the products to the reactants will always be the same. If you're interested, down below, they go through the math of how to work through this. So this is a good place to reference when we are doing some equilibrium constant problems. And then looking on the next page, we have our K's, and so let's do a really simplified view. Our reactant A and product B, and our equilibrium constant would be equal to the concentration of the products over the concentration of the reactants. So if K is very large, which means it's greater than 10,000, that means the concentration of the products must be much larger than the concentration of the reactants, and the products are favored for the reaction. So we have a lot more products than we have reactants at equilibrium. And if K is very small, if it's less than 10,000th, that means A is a lot bigger than B, and that means the reactants are favored for this reaction. Looking at a couple of examples, we have hydrogen and oxygen react to form water, and then you can see our equilibrium constant is 1.4 times 10 to the 83rd. So this is very large, and the products are favored. And we know that, yep, when we have hydrogen and oxygen, basically all of it reacts to form water. And if we look at another reaction, calcium carbonate, reacting to form calcium oxide and carbon dioxide, we have K equals 1.9 times 10 to the negative 23rd. And that's a very small K, which means it doesn't happen very much. So calcium carbonate, if we see at 25 degrees at room temperature, very little calcium carbonate will decompose. And so it really favors the reactants, and it'll mostly just stay as calcium carbonate. Let's solve an equilibrium constant on our own now. To solve an equilibrium expression problem, first off, write the equilibrium expression. Then we're going to substitute in our known numbers, and we're going to solve for the unknown quantity. So scrolling up here for a second, you may be solving for the constant, or maybe for one of these concentrations. So please write this down. Given our equilibrium constant, KEQ, is 50, and the molarity of hydrogen is 0.22 molar, and the molarity of iodine is 0.22 molar, solve for HI given this equation. Hydrogen gas reacts with hydrogen gas, iodine gas, in a reversible reaction to form 2 moles of hydrogen iodide gas. So please write that down, and then let's work on solving it. The first thing we're going to do is we're going to write the equilibrium expression. So please write this down. KEQ equals the, we're going to write down this thing, and then we'll sub in our numbers. So let's talk about that. Our product is hydrogen iodide, which is here, and we're solving for that. So that's going to go up on the top. And then our reactants are hydrogen and iodine. And the molarity of hydrogen is 0.22 molar, and the molarity of iodine is 0.22 molar also. And our KEQ is right here, 50. So let's sub in our numbers on the next slide. I've subbed in the numbers, and yours should also look like this, where we have our equilibrium constant of 50, our unknown, and we know that This is squared because this coefficient is 2 there. And then we have our concentrations of our reactants. And they each have a coefficient of 1, so it's just to the first power, or 0.22. And now this is simple algebra. So we're going to solve for our unknown here. So the first thing we have to do is we have to get rid of this. And 0.22 times 0.22 is 0.084. And whatever we do on one side, we're going to have to do on the other. So let's do that. I have subbed in my numbers. As you can see, I took 0.084 and times it by each side. And then we know that those are the same number, so they're going to cancel out. And then 0.084 times 50 is 2.42. And then I'm left with the molarity of the concentration of hydrogen iodide squared. And we know to get the concentration of hydrogen iodide by itself, we're going to have to take the square root, ooh, that's rough, of 2.42. And then we get 1.555 equals the concentration of hydrogen iodide. And let's look back up at our equation. And this one has 2 sig figs. The equilibrium constant we're not going to use for significant figures. And this one has 2. So then we'll put our answer in 2 significant figures, which is 1.6. And our unit is molarity. And let's double check our answer. So 1.6 molar is the concentration of hydrogen iodide. It says given KEQ is 50, solve for the concentration for hydrogen iodide, and we did that. And looking here, 50 is bigger than 1, so we think that we will have more products at equilibrium. The concentration of the products is greater than the concentration of the reactants if this number is bigger than 1. So let's look down there, and it is indeed bigger than 0.22, so that's a reasonable answer. Good job. So that concludes our Chapter 12, Section 2 notes, and I will see you next time. Bye.